Hello, everyone. I'm going to discuss section 6.5, periodic variations in element properties. The learning objectives for this section describe and explain the observed trends in atomic size, ionization energy, and electron affinity of the elements. This should also include the size of ions, which they might be um, thinking of as a subset of the atomic size. So we're going to talk now about some of the trends of the periodic table that we've been alluding to all semester. We'll get into more detail on the bonding characteristics and how some of the trends we'll talk about in this lead to those characteristics in the next module. Um, but my hope is that you don't approach this as memorization, but as with your understanding of the periodic table, it makes sense why you would have the trends that you do. So that's how I will be approaching this subject matter. So let's go ahead and start with the first trend, which is the covalent radius. So we want to be very particular when we talk about atom sizes because depending on the context, the atom could have a different size. So the context we're using here is when we have a bond between generally two atoms of the same element or something to that, something similar to that, we define the covalent radius as half the distance between the nuclei. Um, and so that's how we're defining it here. Later, we'll look at other ways to talk about the size of atoms. So we're showing a list here for the halogens. And what you'll see is that as you go down the group, the radii get larger. So starting at the top with fluorine, we have a radius of 64 picometers. At the bottom with acetine, we have 148 picometers. Now, you will not have to memorize these numbers, so don't worry about that. What you want to understand is that they get bigger as you go down. Hopefully, that's pretty intuitive. You're increasing the size of the atom, so you would expect the size by size. So I guess we could use size in two ways. We're increasing the mass of the atoms. We're increasing the number of particles. So it would make sense that those would get larger. So this is a fairly intuitive one. However, we will see they're not all this intuitive. Okay, so here we're showing how we can, again, based on the distance, half the distance between the nuclei, how that is arrived at. So here we're showing kind of the periodic table as a whole, and it might be hard to see all of, the differences in size here, but we can see what we just talked about for the halogens. They maybe, if you look at the very top one and the very bottom one, there's definitely a difference in size there from top to bottom, with the bottom one being smaller. With the bottom one being larger. You can also see if you go across the period, so let's maybe look at period 4 because it goes all the way across. From the start to the end, we can definitely see the first one is bigger, okay? So that is different than the trend we just discussed for the halogens. The first one is bigger. And we can make a plot of the atomic number and the radius. And overall, what we see here is that we have kind of a general increase. So it's generally getting larger as you increase the atomic number. That should make sense. But it's not a linear increase. So there's kind of this up and down that we go through where the up is group 1. So the group 1s are all along the top. There are very few things that are larger than any of the group 1s. So a few things that are bigger than, say, lithium in here, and maybe bigger than sodium. But the group 1s are very large in size, and then it goes down from there. Okay, so that might be different than you expect. So as you go from the left to the right of the periodic table, they generally decrease in size. There are some kind of so we can see kind of decrease in size, jump back up, decrease in size. And then when we're in the transition element region, there is some variability there. We're not going to worry about that variability for this course. Okay, so you basically want to look at this trend. So large and then decreasing, large and then decreasing. The reason for this trend is something called the effective nuclear charge. And the idea here is that we talked earlier about the core electrons and the valence electrons. The core electrons are able to shield the full charge of the nucleus from the valence electrons. So the more valence, essentially how this works out is the more valence electrons you have, the larger the charge they're seeing. So if you have, for example, for something like one of these group 1s, you have one valence electron. So your valence electron is feeling the charge of a +1 because everything beyond that is being shielded. Whereas if you are a halogen, or let's actually go to noble gas, if you're a noble gas, you are feeling a charge of +8 because the other valence electrons are not shielding the full nuclear charge. They're only shielding the previous core electrons. So for neon in particular, the core electrons would be shielding a +2 charge, but they wouldn't be shielding the other +6 because these are all valence electrons. Now there's a little bit of, it's not exactly +6. There is some partial shielding going on. We're not going to care about that in this class. That's something you would learn at a higher level if it becomes important to you. But the idea is that you are, as you increase the number of valence electrons, you're also increasing the charge each one of those electrons feels, so the nucleus is able to pull them closer together. Okay, so as we move from a +1 charge towards a +8 charge, +1 towards a +8, that those valence electrons are feeling, they get sucked in closer and closer and closer and closer because of that. Okay, so that's what we want to understand in terms of explaining why they're getting smaller. Okay, so you want to be able to sort atomic radii based on these two trends. Let's talk about the ionic radius now. Okay, so ionic radius is referring to the size of the ions that form. And we'll generally have the same idea here. The effective nuclear charge is what contributes to this. So if you have a positive charge, your radius will be smaller. So we're showing that here. We're going from, for aluminum, we get a smaller size when we have a positive charge. Again, because you have lost electrons, so it's easier to pull them in closer. Likewise, if you have a negative charge, you're going to have a larger radius. Because you have more electrons, it's harder for the nucleus to pull them all in. Okay, so positive charges lead to smaller sizes, negative charges lead to larger sizes. Okay. We can talk about atoms and ions being isoelectronic, so that means they have the same number of electrons. We'll be talking more about this, I believe, in the next module, but you can see a trend here where they all have the same number of electrons as a noble gas, and that's often going to be the way it works out. Again, more detail on that in the next module. But speaking of ions, when we form an ion, the energy associated with that is called the ionization energy. So the ionization energy is the energy necessary to remove an electron. So I say forming an ion, I'm specifically referring to an ion with a positive charge. So removing one electron would be the first ionization energy. Removing two electrons would be the second ionization energy. So we can think about what trends we might have in terms of how easy is it to take away electrons from an atom or ion. And again, we have a graph that shows that. And what we see here is hopefully what you might expect. If you have a noble gas, it is very difficult to remove that electron. So you can see we have kind of similarly a trend of getting easier. Okay, so these are overall getting smaller, but we always have the highest one as a noble gas. Okay, noble gases are always higher. Likewise, on the bottom, we always have group 1. So the idea here is that the noble gases are very stable. Because they are very stable, it's much easier to remove one electron if you are going to remove an electron so that you end up as a noble gas, right? So going from lithium to helium, that is very stable. That's something that wants to happen. Similarly, for all of the group 1s, if they lose one, they end up as a noble gas. You might remember we said group 1 will tend to have a +1 charge. So that's kind of why that is the case. So hopefully this kind of makes sense. In terms of there's some other up and downs going on here. Those are generally associated with half-filled subshells or filled, either filled or half-filled subshells. So the S full or the S or the P half full is often what's going on there, or something related to the D subshell. So I'm not going to care that you remember those little kind of micro trends, but that is why that is occurring the way it does. And then this is showing the specific numbers. Again, don't try to memorize the numbers. You want to understand the overall trend. So if there's a comparison, you would want to be able to get that right, where the comparison would probably either involve either a noble gas or alkali metal, and then something other than that. So we're looking at kind of the broader trends here as opposed to the micro details. And then we can have additional ionization energy, so removing more and more and more electrons. And you can see as you take away more electrons, that becomes more and more and more energy is necessary for that. So don't worry too much about knowing what these are, other than just know what it means to have ionization energy, 2, 3, or 4, or whatever. Okay, so almost the opposite of ionization energy would be electron affinity. And so this is the energy change by adding an electron. And this is in the gas phase. So if you have a gas phase molecule, how much energy is involved in taking up an electron for that. So I believe there is, okay, they only have this as the periodic table. But generally what is going on here is that, so negative means that it is energetically favorable, right? So that's an exothermic process. And you see that we have very negatives for the halogens. They want to get that electron so that they're like a noble gas. And then also negatives for some of these other nonmetals, okay? So nonmetals want to gain electrons, and that's why we have that as an exothermic process. The noble gases are all kind of very, very close to zero, and those are kind of actually theoretical numbers I think they're throwing in there. Whereas on this side, we have some positive numbers. So that means that it doesn't actually want to happen. And then also kind of very, very close to zero here. These ones, they might do it so that they fill their S subshell. So that's why those are a little bit favorable, but really, really not favorable compared to what we're looking at for the halogens and the other many of the other nonmetals. So those are the trends that we have for the periodic table. So you want to be aware of those trends. And again, the goal here is not that you memorize everything or memorize numbers, but that if you have an understanding of how the electrons want to behave, how the nucleus wants to behave, it would make sense to come up with the answer to the question in each case.